So hi everyone, and hi everyone who is still joining us. So welcome to the online car showroom. I think most of you listening have been to one of these before. So I'm Hannah Baker and I'm one of the directors at Cambridge Architectural Research. For today's showroom, Gary Clark from HOK London Studio is giving the second part of his talk called The Golden Thread, A Personal Journey. So Gary's previous showroom was interrupted by a fire alarm and he was just about to move on to some of his case studies. So it'd be great to hear about this today, and fingers crossed for no interruptions. As Gary said himself, there's no planned fire alarm for today's talk. So Gary will present for about 30 minutes and then we'll move to open up a discussion and questions from you. So you can either raise your hand by pressing the button at the bottom of your screen and then we can invite you to the panel, or you can put that in the question and answer comment box and we'll read it out for you. So the talk is being recorded, but this will stop when it comes to the questions. Helping with coordinate all of this as usual is Natcha, a PhD student in the architecture department at Cambridge. So I'd like to thank her in advance, as well as Janet Owers, who has helped informing people about the new date for today. And of course, these thanks extend to Gary, who has agreed to come back and finish the talk. So I'll pass over to William now to reintroduce Gary for those of you that missed the first part.
Hi, I'm William Fawcett, Chair of CAR. I've only briefly introduced Gary again. Welcome back to Gary. I'm very glad he was able to continue his interrupted presentation. The reason why we're so delighted that Gary has come is that he's a long-standing Cambridge Department alumnus. He was trained as an architect originally, then did the MPhil in Energy and Environment Studies in 1992-93, quite a while ago. He went on to do some further research, then decided that perhaps more could be achieved in practice. He moved into practice, and he's now at HOK, very large international practice, where he has a senior role promoting sustainability across all sectors. He himself specializes in science and technology buildings, but his role goes beyond that in the practice. He's also very active in RIBA and Queen's University Belfast, promoting sustainability. So he's a big figure in the field, and it's a field which you all know is vitally important. So we're delighted that Gary was able to continue his rudely interrupted presentation. Great. Thank you, Gary. Please tell us more.
Okay, thanks very much, William. And yeah, fingers crossed. There's no other things that happen. So the last one was a real fire alarm. So that was I had to really escape, pretty quickly. So right. So I'm not going to go over all the old slides, but there's just one slide that I showed you last time, which will pick up the thread from there. So this is the diagram that we created for the RIBA 2030 Climate Challenge. And what it is to really show a trajectory. I mean, this is just a linear regression from now through to, you see, 2050 is kind of effectively where the line goes down to the zero. And what it's trying to illustrate to our kind of sort of peers and other architects, and to all of us really is how short time is really. We can see here at the left of the slide, this is current business as usual approach in terms of building regulations. We're touching, most of the time we build buildings which are unsustainable, and we know it's unsustainable in terms of its operational and embodied carbon. And then what we're trying to sort of say to everyone is actually we've got to start now in 2021, because the time that we're on the boards now, and generally a life cycle of a project for a larger project is 3 to 5 years. So by the time you design us now on the board, it's 2025. It's going to come into operation, and then we need to be on the way towards net zero, because we can't really, in the big scale of things, we can't build any new buildings that are going to add to the problem. And then also we're encouraging a deep retrofit strategy approach, where really by 2030, all new buildings and all deep retrofitted buildings should be net zero. And that's really then the elephant in the room then is we've got to deal with the 45 million existing buildings that are the worst performing in Europe. So the point here is really saying, start now. 2025 is coming around the corner, and it only really gives most design teams about 2 iterations to get to a point where, you know, we were delivering net zero in practice. So that's really the urgency of the situation. So I'm just going to give a few moments, really. Well, that converts, sorry, this to this, which is actually our kind of targets. So this is kind of the version 1 of the 2030 target. And what I was trying to do here is to show the balance of operation and embodied carbon. and our point is really, or my point is, you can't take the eye off the operational energy side of the equation by focusing on embodied carbon. There's a big move towards whole life carbon, which is actually sort of saying, well, embodied carbon will be the bigger factor of it because we've solved operation. But I think, as everybody probably in the field knows, is if you take your eye off of operation, then quickly that could still be greater than anything to do with embodied carbon. So again, it's just showing the story of how we get to zero with a twin focus. So I'm just going to show some examples of how I've tried and came close over my career, and it's then 30 years. And I would say I'm not satisfied. So again, you know, I've came close, but again, it's just extraordinarily difficult, and I'm not finished yet. And really, with the work at the HOK and obviously trying to persuade others, is that we've got to do better. And we're going to do it more consistently. So just one thing before I move on is this is the best performing in terms of Billboard S and others database, build performance database. This is the best performing non-domestic higher education building in the country, and it's been over since it's been completed. So these are actual data. So it's 70 kilowatt hours per square meter, which is a 68% reduction from our 2030 target, which is actually within that window. We're trying to get down to 70 to 75% reduction before you factor in renewables and offsetting, and that's probably where we think the sweet spot is for non-domestic buildings. But that's without renewables, so there's no PV, and there's also no heat pumps in that as well. It's a passive house approach, and it's a fantastic building. So again, I'm sure you know it well from Cambridge. Anyway, that's our target. How close have I came? Well, not as good as that, really, I'm afraid. The final bit was really this: is that all that data is going to be in the awards as well. So first one is when I left. When I left academia, I sort of joined Hopkins Architects and really sort of shared my philosophy in terms of the expression, especially natural ventilation, and how to use that for meaningful expression of architecture, but also to achieve low energy buildings. And my first project was with this small pavilion in St James's Park in London, and it was an earth sheltered building, and the reason was is the very kind of high scrutiny in terms of planning from both the mall and around. It had to be a very low profile, but obviously part of that earth sheltering is very much kind of an ecological sort of approach to building in terms of low profile, low impact. But obviously there's a kind of story to that in terms of body carbon. Effectively, what it is it follows the listed paths of Nash. So the front curve of the building follows that path, and that line is actually listed. So that's why it's that shape. And then what we did is we had to weave that between the existing trees, which we couldn't obviously risk knocking down, and that then generated the whole sort of concept of the building with the path weaving over the top and through the trees. Then we were trying to make this wholly of timber, again, for obvious reasons in terms of embodied carbon. And then we went through a whole exercise of choosing what type of timber, but we wanted a timber that was going to age gracefully, obviously no petrochemicals in terms of its preservation. And there's only a few timbers that obviously hit that bill. This was larch. Now, the larch in the UK, unfortunately, is a bit too fast growing. It's good for cladding, but not for structural purposes. So we had to go to Austria. So it's a high altitude larch, which then grows slower, more dense, and you can see the density there. And we worked with SFC to choose a forest that was managed by multi-generational Austrian family. And again, it's a very sensitive approach to kind of cutting trees down. This is an old growth. This is part of their managed forest, and then they plant 2 trees for every tree they cut down. These are when it's sawn into the major planks, and then this is the finished building. So we can see here the kind of the front of the building, all timber structure, everything about it, and really this is obviously when it was completed, when it was still quite honey color, lovely color, and it's been left. It hasn't been coated, and it's been left to silver. But unfortunately, what happens in city centre pollution is the actual particulates in the air actually darken the timber a little bit. So so it actually it's not silvered as well as we'd hope. I think if it was in maybe rural Cambridgeshire, it would look even better. But the idea here is using basic principles. It's facing a south east location overlooking the lake, and then really setting up layers where you set up this engagement with the public where they can interact, sit in the building. Then you create the loggia, which is then sort of this kind of sheltered area, providing shading as well. And then gradually going into the various layers of the building. And along the top, there's a walkway where people walk over as well. And then this is the plan here. So we can see it's a folding of the landscape over the top, and then actually the path underneath it. And we can see the plan, how it basically just creates a clearing into geometries, really folding and creating a space within the woodland. And see, this is the view from the terrace. You can see from the outside, and then gradually coming to the rear of the space where the servery is, where it's kind of the front of house and back of house area, and introduce roof lights as well to try and balance up the daylight and get really great, fantastic light. So again, you can see here some lovely light quality. And this is the shop which kind of really pleased with. This part front of house is all naturally ventilated, and then it uses the kind of the kitchen extract, which is then in terms of thermal recovery. That's how that kind of drives the major ventilation strategy. And obviously these are automatic vents at the top there, and then the manual sliders. And again, it just provides this kind of lovely spot in London, and it really kind of embodies this kind of sustainable aspect, which is that okay, operational energy is one thing embodied. We see there we had to introduce some concrete because of the weight of the soil above, but again, it's this whole thing about health and well-being and this regenerative restorative design principles as well, creating a lovely place which will be sustainable because people love it and they will hopefully use it for many years to come. So that fed into another project which crossed over with Bill Dunster on this project. So this is kind of fascinating side of it, and Jubilee Campus, Nottingham University. And it was taking a brownfield site, which was the Raleigh Bicycle Factory, and then creating a new campus for Nottingham University. So these are the pavilions that were created, and it was actually a concrete structure with a 50% GGBS cement replacement, which helps a little bit in terms of the body carbon. But actually all the kind of facades were actually, this is Western Red Cedar from Canada. Again, the same principle, again, trying to make sure that it isn't coated or painted or whatever. But behind that is actually the warm cell system, which again is chopped up newspaper with a borax solution, and it's breathable facades as well. And a very kind of simple mixed mode system where we've got openable windows, but then behind that we've actually got a mechanical system as well, which I'll go into in a minute. So fantastic space. And this was again an early sketch. I'm not sure from Bill itself, but again, this is where I picked up. And we can see there that the atria between the spaces, that's a buffer spaces, providing that kind of preheat towards some of the academic spaces to the side. And then that's free venting. And then actually had, in this case, it was a wind catcher, a combined wind capture and extract over the kind of the main cores, which then helps drive the actual mechanical ventilation. It was then developed a little bit from less the wind catcher, but you can see here a diagram of this package plant, really lovely design, working with ABB in terms of the bespoke plant, a big thermal wheel in there, and then really incoming air coming through that, mixing obviously with the thermal recovery with a ventilation bypass towards the rear, and then the wind cowl is then sort of reducing that velocity just to maintain that negative pressure. So again, the thing here is the university, this work, it's really expression of this kind of natural ventilation, which is a very much part of my early kind of work as well. So that's why I was naturally drawn to Hopkins. And this is the final shot in the front. This is the business school, the last phase on that. So we were using soft landing principles, working through in terms of looking at the previous phases. It's slightly different in design is that the client, I mean, I started off saying, well, let's build another version of another one of these pods, but the client wanted the larger building for the same cost, and it'd been 5 years different. So again, that's why we lost a little bit of the wind cowls. But again, working with Arabs, we managed to kind of minimize the reduction in energy use because of that, but using the same principles again. So all that can then fed into another building at Hopkins, and this is one of my last ones there. It was Applied Research and Development Center at Northern Arizona University. And it's quite an odd assignment. So this is where the university, they'd actually, the estates director was at a conference in Jubilee campus, loved it and said, I want these guys to build, you know, our new building. And they wanted the greenest building in the world at that point. So again, it was a big challenge, that one. And this was a lovely facility which was taking all the kind of ecological and biological departments in terms of postgrad and research, and put them into one building. And again, it's that incubator type approach where all those ideas would actually be cross-referenced. So it was really kind of a real kind of center for that. You know, when we actually did the competition, I calculated our carbon emissions of flying out as a small team every year and every couple of months to do this. And you know, again, the benefit of the reduction of the energy that we were aiming for the building, that would far outweigh anything we were traveling with. So I think we had to be very sensible about that in terms of how we do it. But we work with the local architect as well, so we didn't travel over too much. But now, in terms of teams, it would be actually so much simpler. So this is the sketch I did the night before the interview, so which was really sort of picking up. There was an existing flood detention basin there, so I was using this for some, evaporative cooling on that one. Obviously, this is a poetic license in terms of taking it into the building. You'll see that didn't happen. And then really using the principles of what we'd used on Hopkins before is you got this kind of central core of a heavyweight building for that thermal mass, linked to kind of sort of heat in terms of ground source heat pipes, and then sheltered with a kind of atrium type space. And this location was facing against southeast rather than south, but it's quite high altitude in terms of Flagstaff. It only reached about 75 and even in midsummer, so it's 7,000 feet up. So again, the climate was very much closer to a UK perspective. And this is going to approach it at the base there. It was just this layering effect, creating a street where you have kind of interaction of all the departments and all the staff there, movable green screens as well, and then other departments kind of fanning out towards the north there. So it's almost kind of shop fronts. And this is the section a little bit more developed here, showing the kind of terrace. And we used kind of obviously examples of other Hopkins buildings in terms of this is dynamic earth toward the bottom left. We've got Evelina as the glazed atrium. We've got the Forum in Norwich, which is another one of my buildings, using that kind of concrete finish. And then we've got aspects of the of Jubilee campus there, creating a kind of a lovely kind of section. You won't obviously be able to read any of this, but this just shows you even back then, it was basically the entire sustainable outcome cycle was all considered with ARIPS, our engineer. So the entire life cycle, even the water cycle of how we dealt with rainwater was all very much part of that mix. So it's all integrated. So, great project and good delivery. This is a couple of shots of the finished, we can see there, this is the atrium facing south east. And again, all the external louvers were tuned absolutely to that direction in terms of orientation and size and so forth. And then the inside of the space as well. So getting a good quality of daylight in there with no lights on, and then gradually coming back into the departments there. So again, really lovely building and well loved. I think that's the thing. Oh, one final thing is the timber you see there. Obviously, I tried to do timber on the outside, and it was a very curious thing where it's different cultural perspectives. Obviously, we're trying to use much timber in UK, but the more green fraternity, especially in the mountain areas of the States, they were very sensitive to use timber because they really know that there's been quite a lot cut down. So again, it's really avoiding the use of too much timber. But we actually managed to get this timber glulam in. And this is actually the result of glulam timber of trees that were caught in a fire. So this is kind of the redwood fire, and they were actually sort of salvaged. The core of it was still okay, and they were made into glulam. So a lovely story of using some of the timber there. At the end of the thing is we did deliver in terms of from a LEED perspective. This is the highest LEED rating at the time, so of any building, and I think we almost got full. I think at that point it was 62 was the maximum, or 64 was the maximum. So we got that kind of LEED platinum. And then in terms of energy use, and this is part of the story which I'll come on at the end, is despite me really being keen to find out in terms of post-Hopkins evaluation of the buildings, it's very difficult to go back into our completed buildings, which will come on to the end. Then I left Hopkins, go right back to Scotland, for a number of years, and so I worked at Rad Bennett's, and so this is a couple of buildings I worked on them. I came in at the end of this building, and again more on the kind of soft landing side, finishing off the project, and it's a fantastic project, School of Informatics in Edinburgh, and we can see here this is the diagram, which is very simple. You know, again tuned in terms of the depth of the building, large atriums in the centre, which then are our stack drivers. And it's a mixed-use scheme as well, but really trying to get that nice quality of daylight throughout the building. You can see here, this is very, very lovely, very active frontage as well. So very picking up similar principles of the R building in Arizona. This is our environmental diagrams, again showing the classic sort of stack effect. I think I was a bit concerned. I think it's worked out fine in Edinburgh, but a bit concerned that we didn't have much of a reservoir at the top there of the atria. But I think in net result they used, again it was Bureau Happel, this engineer, which used a bit more fan power to make sure that didn't overheat in the top floors. But again, it worked well. Lots of tuning issues when we were doing the handover. So again, it was very in-depth kind of sort of discussion, especially trying to balance up the displacement and ventilation system. And this is a view of the inside. Really fantastic spaces throughout, and you know, again, well loved. So again, the sustainability, everything's kind of there. It's a lovely building, quality of light, good health and well-being, and an asset to the university. So it really is seen as one of their kind of best buildings. This is a small project that didn't unfortunately get built. That was in the last recession. So I've got more projects that have actually been designed than built. I think it's the reality of practice. But this was a project which is great. So this shows that they're, you know, right in the foreground, and you can see some wind cowl. So all the kind of lessons and all the things I'd really be keen to build was really kind of integrated into this project. So this is a commercial office building, and this is what it looked like when we found it. And the client was great. It was an ex-architect who really wanted to say, like, okay, rather than knocking this building down, let's see what we can do, retain the embodied carbon, save all that embodied carbon, and try and, you know, show as a showcase of how you can, you know, retrofit, do a deep retrofit to an existing building, and actually make it attractive and make it really sellable as well. So what we did was we clipped on a new core, you know, just cleared out all the kind of existing things in the building, and then created more open, flexible floor plates. And working with Max Fordham's in this one is actually really stripped it all back, exposed concrete. And actually in this one, working with Max Fordham's, and they did some CFD analysis as well, is we said, right, this is a naturally ventilated office. Can we do this in a city centre, busy city centre, with all the pollution and noise and so forth? And you know, in terms of the modelling, I think we could do it, but it's a shame that we didn't manage to finish it in the end. But there we go. And this was the kind of the net result. So remember, this is back in 2007. You can see here. So we were trying to head for the 75% reduction in CO2 emissions. We talked about natural ventilation being possible. We were looking for an A-rated, obviously EPC, BREEAM excellent. And then the budgetary was interesting. We saved about £400 a square metre by retaining the frame. Not only that, obviously the embodied carbon as well. And the running cost, because of the more natural ventilated approach than the conventional mixed mode or mechanical approach, we thought we could get some really significant savings there as well. So unfortunately chalked down to experience, and then really onto taking all of those kind of things, still keeping all those lessons in terms of the various other firms. I joined Wilkinson Eyre back in 2012, back to London, unfortunately, with the recession hitting hard in Scotland. And but you know, again, great fun in terms of working on some fantastic buildings with Wilkinson Eyre. So this particular one, another academic building, this is for City University Law School. And this is the kind of tower on the corner. We can see this is a triple ventilated glass tower. Working with Chris Wilkinson, obviously fantastic architect. Chris is very much kind of sort of a Miesian mindset in terms of doing these crystalline towers. And so this one was a difficult one for me in terms of that isn't my natural, you know, architectural kind of philosophy. But it was a challenge in terms of how could we make it work with building regulations to a U value, and we were trying to get a 0.1 U value on that glass tower, which was extraordinarily difficult. So we're really trying to hit everything in terms of this kind of passive ice level of kind of sort of envelope design, plus trying to achieve that in terms of the kind of aesthetic. So how did we get on? Well, the first thing is the Wilkinson Eyre won this project primarily because they were the only firm that actually was going to keep some of the existing buildings on site, which is quite extraordinary when you think about it. So the pink ones were demolished. They were pretty poor and fatigued concrete buildings. But the two blue buildings were the best, and 1920s and 1890s building. So that was it. And so we basically used that as the primary thing, and then completed the urban block with the new building. So we can see here the plan. So if I just use my pointer, this is the kind of the 1920s exist building, 1930s probably, and then 1890s towards the back. And then we just completed the building, completed the urban block by creating the new building along there, new entrance towards the side, and then trying to kind of build up that kind of sort of that kind of density and the urban feel to it. This is the kind of space in the center. Again, similar thing of keeping that daylight in the inside, but we had to mediate quite a lot of existing buildings. You see to the left, that's existing kind of building. Reglazing it and then making it more of an open plan area was great, and it adds that character and this kind of richness of kind of real material in there as well. The brick was on show, and it adds this kind of dense, this kind of real feel to it, contrasting it with very simple kind of just white plasterboard, exposed concrete again, and then we've got timber acoustic panels, and then just a nice stone finish for the floor. In terms of its environmental strategy, this one again using all the similar passive things, and but it's linked to two actual sort of open source boreholes that go into the aquifer under London. And quite frankly, I don't think I would do it again. I think it was so complicated, and then there's still a risk that the yield from the open source wouldn't achieve the kind of what's required. So there's actually a backup air source heat system on the roof as well. So it's extremely complicated. But this story is an interesting one where we started off as mixed mode, and I was trying to push the engineers, who I won't name on this building, and trying to sort of really kind of open up sort of some of the ventilation towards the outside, the lower use buildings in terms of our offices for professors. But then, really it was a case of, and this happens quite a lot, is actually the computer modeling says, well, it's better to actually do a seal building and do thermal recovery than actually starting to do mixed mode or even naturally ventilated buildings, which is a bit frustrating. And then what happens is you can't, the cost of doing a mixed mode, so having all the mechanical systems, low pressure drop as well, so huge ducts, and opening windows is a double cost. And then this went through a quite severe VE phase, and then something drops out. And so invariably, and this has happened to me a couple of times, is that the opening windows get chopped out. So it's a bit frustrating. It's a lovely building, but for me to not have a building which has opening windows is a real frustration. And actually, that's something I'm really pushing against in practice. So I think any research that helps on that, I think that would be really great to hear. And this is a shot from the outside showing the kind of 90s, 20s, 30s building, and showing the tower from the other side. The tower is extraordinarily difficult. We had to get some experts from Germany in triple skin facade to come in to prove that the overheating risk wasn't going to be a problem, and that was actually through the engineer who ran it through their own building physics department as well. So they created a problem we solved eventually. But my lesson learned in this one is really, and obviously passing this back through to Chris Wilkinson and others who love glass buildings, is it was extraordinarily difficult, almost didn't get through building regs currently, but the next iteration of building regs, I would argue that it's almost impossible to do 100% glazed building. And I think that from my perspective, I think that's a good thing. Then final project with Wilkinson Air, which is then building all those themes. This wasn't built in the end as well, but this is my further education college for Wembley College, and we can see here this is kind of the competition drawings. There was a base of double height. You can see a podium level. And beneath that was all the engineering workshops, foyer entrance rooms, and then because it was an urban site in Wembley, we put all the kind of rooftops were all kind of sort of planted, and space for the students to exercise and hang out and things like that. And we got the podium level, which is all the in terms of the main spaces of the college itself, in terms of social spaces, and then the departments were stacked above that, and on the top floor there was a sports hall as well. So that would have been a fantastic project, and at the same time we won it because once again we were the only firm that said let's try and keep the existing building on site, and that's shaded in red here, and we clip on other pieces to it. So to the left you can see clipped on. And then to the right, we can see that we created an atrium space, clipped on a kind of new structure on there as well. And the engineers were adept at that. We were looking at sort of strengthening some of the columns. It was a good structural, concrete frame, but using techniques of bonding on carbon fiber, you can actually reinforce the building quite sensitively. And then this is the kind of diagram which pulled again all the themes that we've just been talking about. So this had everything at it. And the aim here was to try and hit our 2030 RBA challenge, plus a decade. And then again, Max Fordham's were the engineer. And again, all the modeling was looking good. So it was all really good in terms of models. And unfortunately, there was a problem with the lease of the site. And obviously the pandemic came in as well. So I believe that's now been shelved at that point. So again, another near miss there. And then what I do is, so obviously my kind of sort of still my passion about measuring things. I try and keep a record of all the predicted and actual energy breakdowns of all the buildings I've worked on. And so I've got my own little database. It's benchmark to Billboard S's database. That's why the carbon emissions ratings are 0.19 and 0.46. I just convert back, but now I'm going to reuse everything in terms of just energy. So I've just plotted against Hopkins and Bennett's buildings against this, and then really said, okay, the TM46 benchmark is 75. In the old days, 75 kilograms CO2 per meter squared. Obviously, it's before the rapid decarbonisation, the grid, and we got to hit 75%. So just looking at where we are on our journey. And we can see that generally Jubilee campus, did pretty well. Now these are pseudo predicted. So there's basically, it was working with Arabs at that point. We were, using benchmarks, Econ 19, and then looking at sort of some of the real world data that are coming out. So again, it's pretty close. So I think we can see there. But this is actually just for the regulated energy. That doesn't include the greys, which are the unregulated. So I think from this one, you can see quite a few things there is that they're hitting the 75% for regulated, but again, the unregulated energy takes us over that 75%. So it's kind of quite an interesting diagram. So that's that one. And then obviously I did it for Wilkeston here as well. And topically, your Northwest Cambridge, which is obviously quite close to that. So I'm sure you guys know more about it than I do now. But that one is obviously predicted. So that's why it's grayed out. And obviously at 0 was the target. But again, obviously, I know there's some issues with the CHP engine currently on site. And so I'd love to get back in and find out what the real energy use of Northwest Cambridge is. But you can see there again, it's like the regulated was doing quite well in quite a few of the Dyson buildings, the Wilkeston Air buildings, including our Dyson projects for Dyson, which had one of the largest kind of sort of ground source arrays in the west of England. And then really coming to Oxford Earth Sciences towards the bottom right, that's where we had measured data. So that's why it's all dark. So the regulated was at 15 kilograms CO2 meter squared using these kind of carbon conversion factors, and that's 46 kilograms CO2 per meter squared. So that's going to around about the 150 kilowatt hours mark. So doing well, but not quite there. Then just a couple of things on HOK just to finish off. Been here a couple of years. I head up sort of science technology sector, but also oversee sustainability for London Studio as well. And it's really joining a global firm and actually with sustainability at its heart. So the old chief exec, Bill O'Dell, 20 odd years ago, wrote his own handbook of sustainable architecture, and that was mandatory reading up to about 10 years ago. So there's still copies in the office. So the HOK really do believe and really try really hard to deliver on sustainability, and it's extraordinary. This is the AIA 2030 data. So for 10 years, the AIA has asked for kind of sort of all the practices that sign up to it to actually submit and disclose the carbon emission savings of all their buildings. And you can see this is all the main studios around the world. And we see London there. And last year, 2019, we predicted to have 61% less carbon emissions in our buildings, but it's using ASHRAE 90.1 as our benchmark. But this is all predicted. But the 90.1, I must say, I'm quite using that with our American colleagues. I was quite surprised, but it's closer to more of a TM54, which is closer to reality than perhaps some of our own Partel debates now. So anyway, that's all great. And then finally, it's just really the buildings from my sector. So top left is the Glasgow Advanced Research Centre. That's being completed just this month, handed over, it'll be open next year. And that's similar to our building for Edinburgh and also for Northern Arizona. It's a cross section of research departments coming together. Some fantastic stuff is going to happen there. And then in the lockdown, the bottom left, I picked up one of the mega labs. So this is the largest diagnostic facility in the world. So it is actually, we repurposed an existing warehouse. And then within a year, it's all finished now. That we picked it up last October, and the first lab line was handed over within sort of 4 months, and it's actually already processed 1 million COVID tests. So, and this is kind of sort of some of the shots there. And then the final two really is some commercial lab buildings. So this is a building just next to us in Tottenham Court Road with Pearson & Co. So it's a lab-enabled commercial office. And then we've got the picture below that is for Sutton. Now, the two of that, what I've done is I've picked up through the lockdown. I got some of our really great, fantastic modelers, physicists in the studio to run some scripting. So this is kind of the script behind it, but we've been running optimization strategies to see how close can we get a lab to net zero, and how close it is. So the benchmarks we used, again, there's very few benchmarks for labs, unfortunately, in the UK. So there's S Labs. There's a study done about 10 years ago. We can see it there. And roughly it's about 600 kilowatt hours per square meter. Contrast that with the American I2SL, which they've got 1,000 labs database and really sophisticated, one of the best I've seen. And really the average of that is about 900 kilowatt hours per square meter. So really large and high intensive buildings. And then really we're trying to aim for that 75% reduction. So you see that we're trying to get to 147, including on-site renewables. And the 2030 challenge is really saying, well, look, that's probably a good balance point if you can get that close. And then you're allowed to offset. But there's a whole debate in terms of what offsetting is. We say that it should be gold standard, it should be meaningful, it should be local, regional. But again, so how close can we get to that? So that was our study. And operational energy, we used online tools, Energy Plus, Honeybee, and so forth. And we did just a kind of optimization study. So we got to around about 60% reduction. And this is the first cut. We're going to run this again with an IAS model probably in a couple of months' time. And then that allows really, what we're saying is we need 15% renewables. But again, the air source heat pumps obviously counts for that, as well as some PV. But in dense urban situation, obviously it's quite limited in terms of how much you can integrate into that, and then allowing that 25%. So we think we're in the right ballpark for operational energy, ventilation being one of the critical things. So that's going to be a specific study that we're going to do next year. And then embodied carbon was kind of quite interesting. So this is, we run 3 different models. One is a base case, which is very much conventional. It's in situ concrete, precast concrete panels with installation, and raised floors, suspended ceiling, so forth. And you can see that L base there, so the baseline, and that worked out about 44% reduction from the benchmark, which is 1,400 kilograms CO2 per meter squared, which is probably pretty close to where we all are. Then we run a different version, so saying more precast concrete, trying to lighten the structure, using a bit more steel rather than in situ. The conventional theory is obviously in situ is the worst case, but actually that was interesting. That showed a higher embodied carbon, mainly due to the amount of kind of steel we had to put in. And it's all about the vibration analysis of lab buildings. We need to get to the vibration criteria of a operating theatre, for instance. So that really increased. And the final version was all timber. So this is where we used structural timber, glue lamp columns, beams, CLT floors. We had to introduce a screed topping on top of the CLT to minimize that vibration criteria. But again, that was fantastic. That got down to 60% reduction. But interestingly, this is before sequestration. And again, there's different models. The American version, they don't include sequestration because they say, well, how do you know that carbon that you've locked into the building is going to be locked there forever? You don't, unless there's a kind of maybe something written into the lease. But if you include sequestration in our 2030 challenge, and the RBA and also Letty do that, if you include that, then actually it's phenomenal. It reduces it by 400 kilograms CO2 per meter squared. So we get down to 150 kilograms CO2 per meter squared, which is almost that kind of golden target of net zero. But the thing that we need to think about is MEP, the embodied carbon of our MEP. I think it's infancy. I think it's a lot of work still to do on that. So that's really what we're trying to aim for. So that's current hot off the press. That graph was done on Monday. So just finalising and pulling up a few threads. So these are the responses that, taking all that kind of sort of theory and practice and trying to put that back into policy. These are the things I've written for the RBA, which has then gone back into government. So these are a set of recommendations that we've been lobbying. First one is, really, you can see here is targets trajectory. What we've been saying is the government's got to acknowledge that we need to set that trajectory, and the 2050 in the COP26 for me was really just it was a bit frustrating. Boris and most of them are trying to solve the problem by the energy supply, and they forget about the energy demand reduction that you need to do it. I think you can't achieve the former without the latter. So we're trying to get our 2030 challenge written into the new building regulations, trying to also say it's in-use verification and performance targets. You can't just use prediction methods. Trying to get the government to do the net zero retrofit or the Part Z sort of part of building regulations. And again, that's a very big thing that I think we've only seen the government just dip their toe into. And then just specifically saying about EUI targets and design for performance tools. And we know they've picked up the design for performance tool because we understand that they're actually working in the background on that. So I don't know much more than that, basically. And then trying to include embodied carbon in the new building regulations. Again, we've heard some positive noises on that, and then some colleagues presented to select committee last week on that. So hopefully that's going to come through. But notwithstanding everything is in the previous rush to net zero back in the early 2010s, we've got to think about good health and well-being. So again, it's just that thing about in-use verification, overheating, plus obviously indoor air quality is absolutely critical. And it needs to be integrated policy. Planning and building control have got to be done together. And if you don't have them together, then that's where it all gets a bit confusing. And then just going to leave you with just 10 things which I say to all the my staff inside, and obviously to colleagues when I'm presenting. These are the 10 things that we need to do now. First one is agree your outcomes with your clients. Again, use that metrics in terms of sustainable outcomes. Think about the circular economy. Design for net zero performance. This is a measurement and verification. We've got to increase biodiversity, and for us, it was promoting this kind of 20% net positive gain. Low embodied healthy materials, and again, that robustness and long life comes in there. Not forgetting well building for principles of good daylighting, air quality and acoustics. And then the passive design approach obviously goes without saying, but thinking about that regenerative engineering is really how we work with our engineers. And that's obviously where, again, from the Martin Centre in Carr, I know that integration of the two together, that's how we're going to solve it. We can't solve it alone by ourselves. Saying no fossil fuels, that really for us is the end of that particular phase. And then finally, to close the loop, is to design for POE and actually carry out POE as well at the end of the day. So thanks very much.